Hello everyone and welcome to Lecture. Today we'll be talking about some different topics related to extending some of our ideas of uses of parametric curves. And specifically we'll be kind of moving into understanding a little bit more in depth the concept of vector fields. So the first thing that we'll be talking about is what are called streamlines of vector fields. And then we'll move on to the concept of actually differentiating and solving for the rate of change of both scalar and vector fields. So first, we'll start with a couple different, baseline definitions of what we mean by a streamline for a given vector field. So let's assume that we have some vector field f that may be dependent on position and on time. Remember, this means that we'll stick in 3D. The vector field has three components, P, Q, and R, each of which is respectively its own function of position and time. We'll say Pi plus Qj plus Rk. So the x component of the vector field is a function of position and time. The y component of the vector field is a function of position and time, and the z component of the vector field is a function of position and time. Remember, this means then that f itself is a function of position in 3 dimensions. It could be 2 dimensions as well, and it's a function of positive time, and it's mapping to 3-dimensional space in general. This is the 3-dimensional case. In 2D, we have a similar functional dependence, only it's dependent on 2 dimensions of space, and the vector is valued in 2 dimensions of space. So in general, we actually have multiple different types of curves or families of curves that we can study to denote the evolution or the flow associated with this field. The most important for us is what's called the streamline. Or streamlines of the flow. And this is, simply put, a family of curves that are instantaneously, so at each point, in each instant of time, that are instantaneously tangent to the vector field. So, for example, in the case of fluid flow, the streamlines at a given instant of time denote the path that a massless fluid element in fluid dynamics would take in the flow field. So in the example of fluid dynamics, This is the path of a massless fluid element. Or the path of, if that instant, it's the exact path that a massless fluid element would take. This is if the field is constant with respect to time. If it's changing with respect to time, then so are these streamlines. And this is the first real thing that we want to think of when we think of exactly how we would visualize a vector field and the behavior of a vector field in 2D or in 3D. A path line is in general different than a streamline, and a path line is a trajectory that an individual particle will flow This is determined by the streamlines. So you can think of the path line as, a direct, in the fluid dynamics example, it's the exact element, or the exact path, a record so an exact record of the path that a massive or particle with mass will take in a given flow field. And the last thing that we'll talk about is what's called a streak line. Which you can think of as the loci of points of all particles, or loci of points of particles passing continuously from a point in the pass. And this is specifically a path line in the pass. So this is specifically for when the flow depends on time. Right? These three things can be thought of as different when we have this dependence on time. So let's say, for instance, we have a given massive particle that's traveling in some vector field. And this is the path line of said particle traveling through some vector field. This is immersed in some vector field. could be a fluid flow field, or it could be an electromagnetic field. But the idea is this red curve is a path line, say. A streak line is just the evolution of, say, if it's a fluid flow, let's say you release a dye, so this particle is releasing a dye. The streak line is the evolution of that dye as it's released by this particle in the fluid flow field. I think the best way of illustrating this is through an animation. And what you can see right here is in the example, all of these lines denote the vector field at each given instant of time in 2D. This is a 2D example. And the dashed lines are the streamlines, and the evolution of the streamlines as the vector field changes with respect to time. But these dashed lines are the streamlines of the vector field. And you see that as the vector field changes with respect to time, that the streamlines also change. This red curve is the path line of a given particle, or the actual physical trajectory of a particle as it travels through this vector field. You can think of a good way of thinking of this is a flow field, so a fluid flow field, but it could also represent an electromagnetic field as well. So this red curve is the path line of an individual fluid particle, massive fluid particle. And the blue line, or the blue curve that's sort of trailing this particle, you can think of as a streak line that corresponds to this particle. Or if you were to release a dye at every given instant of time, the trajectory that dye is evolving. So the streak line is evolving as the particle flows through this fluid. But this is the main three type of curves that we use to visualize the flow of a given vector field. There are other types of curves or lines that are important in understanding the behavior of a given vector field in different ways. A timeline is an example of one. You can think of a timeline as a collection of path lines. These are the lines formed by a collection of particles. And you also might, in literature, see things that are known as the dye line, which could refer to either a streak line or a timeline, depending on the context. But the idea here is that the most complicated type of flow is flow that depends on time. Now, for our analysis, we're going to stick with relatively simple vector fields to start out with. These are vector fields that are steady. Or constant with respect to time. And what's nice is that with fields that are constant with respect to time, streamlines, path lines, and streak lines actually all correspond to one another, which is very, very neat. And very, very useful in terms of kind of understanding how to actually compute these. But in general, it's possible to, for non-steady flow, determine each one of these. And each one of these types of curves are very, very useful for us in terms of understanding how a given vector field is behaving, and specifically how the flow of that vector field is evolving. So for our first example, we'll use the vector field. It'll be a 2D example. F is equal to, the x component is y, and the y component of the vector field is the function negative x plus y. Or y times I plus the function negative x plus y times j. So in this example, this is our function p, and this is our function q. Because it's in 2D, we don't have a function r. Well, it turns out that for a steady, a nice flow that doesn't depend on time, we can define the streamlines of the curve as follows. This is the collection of lines that satisfy dr dt, or r prime of t, is equal to the vector field f at r. So in general, this is the correct way of defining the streamlines. And in 3D, this denotes three differential equations. The first one is dx dt is equal to p of r, dy dt is equal to q of r, and dz dt is equal to r of r. And this is a system of three first-order ordinary differential equations. This is the system of equations in 3D. In 2D, we only have two ordinary differential equations. The differential equation is dx dt is equal to p of xy, and dy dt is equal to q of xy. And in either of these cases, we can use what we know about the derivatives to actually rewrite this system of differential equations in a way that gives us slightly simpler equations for relating y and x and z. Specifically, we know from our parametric differential equations that dy dt over dx dt is the same thing as dy dx, assuming these are nice enough functions. So dy dx is q over p, and dz dx will be r over p. And therefore, rewriting these equations, we get that dy over q is equal to dx over p. And from this equation right here, we have that the dx over p is the same thing as dz over r. So solving this system of differential equations is the same thing as solving this system of differential equations right here in 3D. And in 2D, we have the exact same process that we can go through here to get that dx over p will always be the same thing as dy over q. So the main idea here is that if we can solve either of these systems, right, either the defining system that defines the streamlines, or this normally simpler system of equations, differential equations, especially if these differential equations are separable, which is not always the case for every example, but if they're separable, we can use these simplified expressions right here to write down the streamlines and actually go through and solve for the streamlines. So let's consider a relatively straightforward example. We'll jump back to our example. And visualization of this vector field in 2D turns out to be relatively complicated, but we can take a look at this and see exactly what this looks like in the following plot. So using either Desmos or GeoGebra or Python or MATLAB, whatever is the easiest method that you want to use to plot out this vector field. This right here is a nice visualization. I'm using Desmos in this plot right here to visualize the vector field, where the first component of the vector field is y, and the second component of the vector field is negative x plus y. You see that this vector field is sort of it's like a spiral. And using a little bit of our theory from an ordinary differential equations class, specifically on solving systems of differential equations, in this example, you see that the system of differential equations that governs the streamlines for this example is going to be dx dt is equal to y, the first differential equation, coming from, for the streamline, dx dt has to be equal to p, and dy dt has to be equal to negative x plus y. So using fairly standard methods from ordinary differential equations and linear algebra, we can rewrite this system of differential equations as the time derivative of the position is equal to the matrix 0, 1, negative 1, 1, multiplied by the position vector, xy. And a little bit later on in the course, we'll review how to go through and solve this, but it turns out that this system of differential equations, linear differential equations, is very, very nicely solved using a little bit of linear algebra and a little bit of our basic what we know about linear algebra. So I'm going to skip over the details of that for now and just write the exact solution to this system of differential equations. Ends up being that x is equal to some constant c1 times e to the t over 2 over 3 times 3 cosine square root of 3 over 2t minus the square root of 3 sine of root 3 over 2t plus c2 times 2 over the square root of 3 e to the t over 2 times sine of square root of 3 over 2t. And y has a similar form. Y is equal to c1 2 over the square root of 3 times e to the t over 2 multiplied by sine of root 3 over 2t plus c2 times e to the t over 2 over 3 times square root of 3 sine of square root of 3 over 2t plus 3 cosine of the square root of 3 over 2t. Whereas C1 and C2 depend on the initial conditions, or the initial point at which we choose to start our streamline. Now, there is a little bit of linear algebra I just want to remind you that goes on in between these steps to get to this final solution. But the point here is I just wanted to emphasize that we can always go through and find a streamline, and sometimes it's simpler to solve the streamlines than others. A lot of times, these rewriting differential equations in using these formula is very useful. But in general, the idea is that we can always, even if we can't analytically solve the equation for the streamlines, we can often numerically solve for the streamlines. And sure enough, what this looks like when we visualize this curve, this streamline curve that we found, is exactly what we would expect from a given streamline. So if I kind of open up and visualize this streamline on this curve, this streamline right here corresponds to C1 equals 1 and C2 equals 1, which would correspond to an initial condition of 1, 1. So x equals 1, y equals 1. So streamline starting at this point right here, for instance. But it's important to note that if you change the value of those constants, or the value of that initial condition, you effectively change the streamline itself. But you see that each one of these streamlines, no matter what the value of C1 and C2 is, or the initial condition is of the streamline, it's exactly doing what we talked about before, which is it's a parametric curve that is following this vector field that instantaneously at each instant point, or each point in time, or in the trajectory along the parametric curve, because it might not be time, is tangent to this vector field. So the next thing that we'll talk about today is the derivative of a scalar field, also known as the directional derivative of a scalar function phi of r. And this is going to be all about, we're going to kind of shift our focus a little bit for the time being away from vector fields and just consider scalar fields, where the scalar field could be a function of 3 variables, This is a 3D scalar field or function of two variables. So the function could map from 2 dimensions into R. And this is the so-called, you can think of stereotypical example being the temperature as a function of position, or the pressure being a function of position. The main idea is that we're going to consider a point R in the domain, and a unit vector u hat representing a direction. In the domain. We define the directional derivative as follows. So the notation comes first. You write a capital D u hat phi of R, and this is to denote the directional derivative of the scalar field phi in the direction of u hat at the point R. This is defined as the limit as h goes to 0 of phi of R plus h times u hat minus phi at R divided by h. And this concept should hopefully be familiar to you if you've taken a multivariable calc course. But we just want to review this a little bit and exactly kind of talk about this for a little bit. This is called the directional derivative of the scalar field phi at the point R in the direction u hat. The reason why it's important to specify all of these is because in general a scalar field, let's say it's a temperature field, will be going from, say, maybe a hot value, values that are hot right here, to values that are cold right here. And then in between, there's a whole distribution of intermediate temperatures. Where it's going from hot to cold, say. And if it's pressure, it could be heavy pressure, a lot of pressure, and less pressure as you move throughout the region. At any given point, R, the rate of change in each given direction, say in this direction U1, or in this direction U2, it could be a different value, and in general it is a different value. So we need to specify and distinguish between, for a given scalar field, the direction that we're taking the rate of change, as well as the value that we're taking the rate of change at a given point. But if this limit exists, we say that it's that the directional derivative of the function phi, the scalar field phi, exist at the point R in a given direction U hat. So the idea is that this is conceptual, and in order to evaluate this, we can go through and actually we try to apply a given coordinate system to figure out exactly what this directional derivative is. Turns out we can always evaluate, as long as the directional derivative exists, we can evaluate it in any coordinate system that we choose. So typically what we do is we go through and we evaluate this using a Cartesian coordinates, if that's the easiest coordinate system. But this, what we've written right here is independent of coordinate system because it's in our vector language. The main idea being the following, though, that if we're at a point R in three-dimensional space or in two-dimensional space, and we want the directional derivative in the direction, say, of the vector u hat, or I'll make u hat a little bit larger. And for small values of h, the vector h times u hat looks like this point right here. And so this new vector is the vector r plus h times u hat. So the difference in this difference quotient is saying that the difference of temperature between this point right here and this point right here, and the difference quotient that we're evaluating here is the difference of temperature at this point and this point divided by h, which is the distance between this point right here and this point right here. So when we take the limit as h goes to 0, we're essentially evaluating the derivative. The directional derivative is just the derivative of the temperature, or whatever scalar function this is, along the line in the direction of u hat. And this is exactly one very nice way of thinking of it. And it's a very nice way of thinking of it because it's actually giving us exactly what we need to simplify this equation. Right, this equation in Cartesian coordinates is saying the following. It's saying take the limit as h goes to 0 of phi of x plus h times u1, comma, y plus h times u2, comma, z plus h times u3, minus phi of x, y, z divided by h. Which is just the derivative, the h derivative, the t derivative of phi of L of t at t equals 0, where L of t is the line r plus t times u hat, or in Cartesian coordinates, it's x plus t times u1, y plus t times u2, z plus t times u3. And you'll remember that this derivative right here is nothing but, we can evaluate this using the chain rule. Right? The phi here depends on x, y, and z, each of which depends on t, from this linear equation right here. Open L1, L2, L3. Well, just do x, y, and z. So d phi dt is d phi dx times dx dt plus d phi dy times dy dt plus partial phi partial z times dz dt, where these are the partial derivative of phi with respect to x times the single derivative of x with respect to t, and so on and so forth for each of these derivatives. This is the so-called multivariable chain rule from multivariable calculus. And what that means is that d phi dt, when phi depends on L of t, is going to be the gradient vector of phi vector dot product with the velocity vector of whatever curve r of t is. And in this example, r of t is just this line L of t, and we know the velocity vector of this curve is the unit vector. So this is going to be the same thing as the gradient vector of the function phi dot product with the velocity vector of this curve, which is just the vector u hat. And what's nice is that u hat is constant. So we have a nice now simplified formula for evaluating the directional derivative. It will always be the gradient vector at the point that we're evaluating the directional derivative at, vector dot product with the direction vector u hat. This is a simplified and nicer formula to use for the directional derivative at any given point. So what we've shown is both the exact definition of the directional derivative, which is the limit definition of the directional derivative, but we've also now shown that this will always be the gradient of the function phi at a given point, dot product with the unit vector u hat. So this shows us a very interesting connection. And in case you didn't see it in your multivariable calculus course, right, the gradient vector is just the vector of first partial derivatives of a given scalar function. The gradient of phi is just a vector containing all of the first partial derivatives of a given function. This is an extremely useful formula. One of the first things that we can actually see about this formula, about why it's so useful, is that it gives us a very nice relationship, and a very intuitive geometric relationship between the gradient vector and the direction that we're evaluating the directional derivative for. By the way, another notation for the gradient that might pop up and you might see is grad phi. Right, this means the same thing as the upside down triangle next to phi. It just means the vector containing all of the partial derivatives of the function phi itself. All the first partial derivatives of the function phi. So this is sometimes called the simplified formula for the directional derivative, but we see very clearly that it comes directly from the limit definition of the directional derivative. And by the way, this is also coordinate free. This is just in terms of vectors. This does not use at all the concept of coordinates. That being said, evaluating this, very often we will use Cartesian coordinates, and sometimes in other cases we might want to express this in terms of polar coordinates or a different coordinate system, which is could be very, very useful. And we'll see how to do that a little bit later on. So one of the things that I'll ask you to remember is, this is back from chapter 6, one of our fundamental relationships for the dot product between vectors, for two vectors A and B. We have that the dot product of A with B is equal to the length of A, or the magnitude of A, the length of B, multiplied by cosine of theta, where theta is the angle between the vectors A and B. This is how we define projections and projection vectors and so on and so forth. But you'll remember that if you take a unit vector and you do A, say, dot B hat, right, that projection vector, this is the projection of A in the direction of B. A dot B hat. Or this distance right here. So another interpretation of this formula is a direct geometric interpretation, which is saying that the directional derivative of a scalar function in the direction of u hat at the point R is the exact same thing, using this formula right here, right, as the projection of the gradient vector in the direction of u hat. Or, in terms of this direct formula, the length of the gradient vector is just the magnitude of the gradient vector at the point R, multiplied by the length of the unit vector u hat, but because u hat is a unit vector, that's just equal to 1, multiplied by cosine of theta. This is the second simplified formula for the directional derivative of a scalar function, and it's very, very useful for us geometrically because of the fact that we can interpret this in a very, very nice manner. This is directly saying that for a given scalar function, at each different point, the gradient vector is going to be pointing in a different direction. This relationship for the directional derivative actually tells us exactly what direction the gradient vector will point. And we can see that as follows, right? We can see that by doing a sample. Say this is the gradient vector for some function phi. And suppose that we have a different unit vector u hat. And gradient of phi makes a certain angle with u hat. Well, using this formula that we've shown, we can see that the directional derivative of the scalar field phi at the point R in the direction of u hat is just going to be the magnitude of the gradient vector times cosine of theta. What does this tell us about theta and about the relationship between the u direction and the gradient vector? Well, conceptually speaking, it tells us that, well, this is going to be maximum the directional derivative is maximum when this is all with respect to a certain point r. So at a point r, the directional derivative or rate of change of r is maximum when theta is equal to 0, because that makes cosine of theta equals to 1. So it's maximum when theta equals 0, or that means that when theta equals 0, the gradient vector is parallel to the direction that you're looking at the rate of change in. At this point, this also means that the directional derivative is equal, because cosine of theta is equal to 1, it's just equal to the magnitude of the gradient vector at the point r. Likewise, this formula tells us that the directional derivative of a function of a scalar field phi is minimum when theta is equal to pi, or the gradient vector is opposite to u hat. This is parallel and same direction. And this should be opposite or parallel and opposite direction. In which case, you have that the directional derivative is actually equal to negative the magnitude of the gradient vector at the point r. And the third and final point here that we have is that the directional derivative in the direction u hat of the function phi at the point r is 0 when theta is equal to pi over 2. Remember that these angles correspond to degrees. 0 degrees, this is 180 degrees, and pi over 2 corresponds to 90 degrees. So if you look at the directional derivative in the direction perpendicular to the gradient vector, that will always be 0. The result will always be 0. And so it's 0 when theta equals pi over 2, or the gradient vector of the function phi at the point r is perpendicular to the direction vector u hat.